Thank you so much, Anton and John. Next up, it's time for you to meet even more of our wonderful experts here today. So first of all, let me introduce to the stage Alice Wells.
Thank you so much, and thank you for having us. This is fantastic. So I'm Alice Wells. I'm a PhD student from the University of Exeter in the southwest of England, and I am researching stratospheric aerosol injection as a form of solar climate intervention. And I'm very happy today to be hosting this panel on preventing Arctic climate risks. So we'll be discussing the governance and state of knowledge of solar climate intervention and opening the discussion on the potential of marine cloud brightening and stratospheric aerosol injection in supporting the Arctic cryosphere. So first, I'd like to welcome to the stage Kelly Wanser. Kelly is a climate innovator and advocate and executive director of Silver Lining, a non-profit organization dedicated to ensuring that society has sufficient information and options to address near-term climate risk. In that capacity, she's helped develop legislation, testified before Congress, developed global engagement efforts, and established a non-profit research program. She was recently featured on CNN, CBS News, and in widely viewed TED Talks. So please welcome Kelly.
Thank you very much, Alice. I'm very honored to be here. My organization, Silver Lining, is very privileged to support Operation Arctis in the organization of this event and the stakeholder workshop they held beforehand. And in the context of the paradigm shift, I think that the young generation of leaders represented by Operation Arctis is very hopeful. And this is, I've been working in this field now for over a decade, and this is already one of the best dialogues that I've experienced. So I'm really pleased and honored to be here, and I'm going to introduce to you a little bit about one potential approach to the paradigm shift with regard to the Arctic. Let me see if I can make the clicker work. And one of the contexts that we're in with respect to the Arctic and global climate change as a whole is the scale of the problem. So one of the things that we have to think about in intervention is what can we do that scales, and that scales along the time horizon that we need it to. So the Arctic is a very big in scale in learning about it. You know, we're talking about an area approximately the size of the continent of Africa. And that's where we're looking at trying to arrest this very big ball going down the hill. So we have a problem of scale, and we have a problem of time. So we're seeing the changes in the Arctic that are happening on average more rapidly than or at the outside of the projections that climate scientists have. And the thing that we know that was referred to before is that the climate system is projected to continue to warm in all of the scenarios that the UN climate change body looks at. So whatever problems we see now, those are projected to get worse currently in every scenario that we've got. And that means we need something in the portfolio that might act relatively quickly at a very large scale. So in the past 10 or 15 years, scientific bodies looked at the question of, what might have the highest potential to reduce warming in the climate system at a very large scale relatively quickly. And where they landed, this was in the US National Academy of Sciences, the UK Royal Society, and more recently in the UN, is one of the ways that the Earth system actually regulates temperature, which is the reflection of sunlight from clouds and particles in the atmosphere. This is a NASA simulation of that reflection as the atmosphere is moving. And what scientists think is that by increasing that reflection of sunlight by just 1 or 2%, you could offset a doubling of CO2 or several degrees of warming. Why do they think that? Because they've observed it. So this is a picture of a cloud bank off the Pacific West Coast of the United States. The bright streaks that you see in the clouds are actually created by particles in the emissions from ships. And you may have heard in the news recently that the International Maritime Organization has implemented regulation to reduce those particles. They come from the dirty sulfate emissions in ships. But one of those things those particles do is have the effect of making the clouds brighter. And collectively, that cloud brightening effect, together with the reflection of sunlight off particles from pollution, all different kinds of that type of particulate pollution from coal plants, from transportation, from ships, the scientists think that that pollution is creating a cooling effect by increasing the reflection of sunlight from the atmosphere. And that cooling effect today, they estimate between 0.3 and 1.1 degrees Celsius. So that's a big range, and it's partly offsetting warming that we would otherwise be experiencing. And one of the things we're getting kind of good at as a society is reducing those particulates and pollution. So we may lose this effect faster than we bring down greenhouse gases. But it's that effect, combined with something else that scientists observe, that have led them to think about whether you might want to produce that sort of effect actively. And the other thing observed is the effect when very large volcanoes go off. And forgive me because my animation isn't here, so I will talk you through it. But when Mount Pinatubo erupted in 1991, it was a big volcano that emitted a lot of particles at a very high force, pushed them into the highest layer of the atmosphere, the stratosphere, where they stayed and circulated for between a year or two. And they observably cooled the climate system by about 0.5 degree until the particles fell down to Earth. And one of the things that happened that they observed after that was a recovery in Arctic ice in the year after the volcano erupted. So scientists have become fairly confident that if you put particles in the outer layer of the atmosphere, in the stratosphere, that you can cool the planet. There's a lot they don't know about what would happen if you try to do that over a longer period of time. But one of the prominent approaches to cooling the planet, including the recovery of the Arctic, is reflecting sunlight by putting particles in that outer layer of the atmosphere by aircraft and seeing whether or not you could maintain that over the course of a decade or two until you've brought down emissions and implemented the other parts of the paradigm shift to bring the climate system back to health. Likewise, with the streaks that I showed you from the ships in the cloud layer, scientists have proposed the possibility of taking a cleaner, more controlled version of that kind of emission from sea salt particles in seawater to brighten clouds over the ocean, and that by brightening certain areas of susceptible clouds, you might be able to produce a global cooling effect. So the question becomes, and the question that was referred to before in research, is could reflecting sunlight from the atmosphere improve safety over the trajectory that we're on? And can we learn what we need to know about that fast enough to make good decisions? And one of the things we need to be able to do, or try to be able to do, is to allow people in different parts of the world to do projections of what the climate system will look like under probable scenarios for warming, and what the climate system would look like under the best possible scenarios for these interventions, with respect to the impacts in their parts of the world and the things that they care about and the things that affect our health and safety and well-being and environmental systems. So that's a pretty tall order in a pretty short period of time, but you're going to hear about some of the research involved in doing that. And if we can do the research aggressively, one of the things that we do to support good decisions is to then have our scientific bodies bring together that information in assessments and put it together in terms of a risk analysis, in terms of the benefits, in terms of what the realities are of what the science and evidence are telling us. And what's happened this year is we've had 3 different governmental bodies recommend that kind of assessment. One of them actually did part of that assessment, the Montreal Protocol that looks after the ozone layer, protects the atmosphere. And they did the first robust assessment of climate intervention in the stratosphere in their chapter 6. I recommend you take a look. And we had 2 really important reports, one from the UN Environment Program and one from the United States Science Agencies, that recommended research and scientific assessment in these areas as a matter of importance. So we think that there's a possibility that we might be able to do the research and conduct scientific assessment and find ways to make good decisions together. And one of the reasons we think that is because we have some examples of our ability to address really powerfully important critical matters of the environment successfully. And the most successful example is the Montreal Protocol that governs the ozone layer. And in the 1980s, when they determined that there was a threat to humanity from the depletion of ozone in the outer layer of the stratosphere, the world came together. They did a lot of quick science and technical work, and they formed a treaty, which today is the only environmental treaty, binding environmental treaty, that has universal participation from all the countries in the world. But it's operating effectively, it's meeting every year, and not only does it protect the ozone layer, but the Montreal Protocol has actually been the most successful in the chemicals that it targets at actually reducing those greenhouse gases and other substances that influence climate change. So not only is it the most successful in terms of protecting the ozone layer, but it's the single most successful human action on climate change. So what we think is that their example of using research, scientific assessment, and broad, equitable participation from all nations of the world is a possibility for decision-making here. But it starts with the science. And so I'm lucky to be on this panel with some of the young, really superstar scientists in the field. And I look forward to you hearing from them.
Thank you, Kelly. That was a fantastic talk. I'm now really excited to present Haruki Hirasawa. Haruki is a postdoctoral fellow at the University of Victoria in British Columbia, where he studies the large-scale climate impacts of marine cloud brightening on global climate using climate models and machine learning tools. He's interested in understanding the large-scale atmosphere and ocean response to human emissions of aerosols, both incidental and deliberate. So thank you, Haruki.
Okay, so thank you. So my talk is going to be about some of the state of the science in terms of what marine cloud brightening could do, in terms of whether or not it could cool the Arctic, and what might the what we would expect to happen if we would apply it within the Arctic itself. And so Kelly nicely introduced the topic, and I want to go into a little bit more detail about what marine cloud brightening is and why we think it might work, and so that ends up being us. So yeah, I'll have to give a bit of a physics lecture, sorry. Okay, so marine cloud brightening is one of the proposed solar radiation management solar geoengineering techniques, and in particular, the idea for MCB is that we would cool the surface climate by spraying sea salt into clouds over oceans. And so this is a cartoon of of what that might look like in terms of the actual deployment platforms. And so this idea, as Kelly pointed out, is it comes out of observations of a current phenomenon that exists, which is ship tracks. And so ships, as they pass through certain parts of the ocean, often leave these tracks, these streaks of bright clouds behind them. And this is due to pollution from these ships, particularly because they're burning a lot of dirty, sulfur-heavy bunker fuel. And so this is, I believe it's in the same region. It's off of the coast of Alaska, some ship tracks in this particular cloud deck from an image from a NASA satellite. Okay, so this cloud brightening effect happens because aerosols are an important part of what of clouds. And so, even in a clean environment, in the natural environment, you have a lot of aerosol particles that already exist in the air, whether it's because of dust or because of natural emissions from bacteria, for example. And these aerosol particles sort of form the core of cloud droplets. So as they disperse into the atmosphere, water vapor starts to attach to these aerosol particles, and over time they grow until they become visible as cloud droplets. And so, of course, these cloud droplets, they interact with sunlight as it comes through and scatter this sunlight. And so this is, of course, why clouds are white. And so what happens under polluted conditions is that you have more aerosol particles, and so there's more places where the water vapor can condense onto. And so as you get these cloud droplets forming, if you keep the amount of water vapor the same, that means you have less water vapor per droplet, and so you get more but smaller cloud droplets. And so this has the effect of increasing the amount of sunlight that's reflected by these clouds, because as you get these smaller particles, the interaction with the sunlight changes. And so making the cloud droplets smaller also has other effects in terms of changing the rate of precipitation, as well as changing some of the how air is interacting with the clouds, and so that can either amplify or diminish this cloud brightening effect. So in the current climate, we're already getting quite a bit of incidental MCB. So shipping emissions are causing quite a bit of these ship tracks, which reflect a lot of sunlight into away from the atmosphere already, and it's believed to have a significant cooling effect on the climate. And this is, but of course, over the years, we've seen a lot of successful regulations to remove these aerosol pollutants from the atmosphere. And this is because sulfur emissions are harmful to both environments in terms of creating acid rain, as well as to air quality as they form particulate matter that are, of course, harmful to human health. And so the idea for a deliberate MCB proposal as a climate intervention would be to, instead of doing this MCB unintentionally with sulfur, these harmful sulfur particles, to instead replace these particles with sea salt, which is thought to be more benign. Okay, so what do we know about what MCB would do to the Arctic? So really the main tool that we have to study this is, of course, still climate models. And it's important to qualify any climate model result by saying that these are uncertain. These are still, climate models are quite complex, but they're still approximations to the real world. And so in particular, in the case of MCB, there's a lot of cloud and aerosol processes that are occurring at scales that are much smaller than what a climate model can capture. And so there's a lot of uncertainty in terms of what might happen as you inject sea salt into these climate models. But what we do know from these climate models is that when we deploy MCB into the climate and we get some cooling, that does, inevitably have an impact on the Arctic, and that's because the Arctic is, as a part of the climate, it's connected to all other parts of the climate, and so even when we're applying MCB in the tropics, which is where we think it would be most effective, that cooling is still being transported by the atmosphere and ocean up to the high latitudes in the poles, and does, according to our climate models at least, indeed restore sea ice. But when we're thinking about what we could do locally within the Arctic, this picture sort of changes in the sense that the type of mechanisms that we would expect to see are slightly different. But there is some reason to believe that Arctic MCB could work, and this is because of a phenomenon known as Arctic haze. And so, since the mid-20th century, we've seen in observations that every springtime, pollution from Europe and North America is transported into the Arctic and forms a blanket of smog that's called Arctic haze. And observations of this Arctic haze have found that during the summer, it does indeed brighten clouds, and it does have some modest cooling effect. But the other thing that these observations find is that during the winter, during the spring, when there's less sunlight, actually this Arctic haze is actually thickening the clouds and increasing the amount of heat that they trap. And so because of the unique situation of the clouds in the Arctic, this means that there's a lot more unknowns in terms of what MCB might do to the Arctic clouds. Okay, but in terms of what the climate models tell us, there's not a whole lot of research on this, but what research we do have does indicate that if we were to emit sea salt into the Arctic, it would brighten clouds in the Arctic, and that would ultimately cool the Arctic and therefore restore sea ice. So this is, for example, a result from one particular climate model where we've injected sea salt into oceanic regions north of 60 North, where there's no sea ice cover. And so this blue region in the bottom panel is showing the amount of sea ice that is being restored due to this MCB intervention. But it's important to note that even though we're putting this sea salt into the Arctic in particular, again, just as the low tropics influence the Arctic, so too does the Arctic influence the rest of the world. And so when we're applying this kind of local MCB, I think it's really important that we make sure we understand what the impacts of these Arctic MCB interventions are on the rest of the world. Okay, so just to conclude, so in terms of the main question that I was asked to answer is, could MCB refreeze the Arctic? And the answer so far seems to be yes, but this is just according to our climate models, and there's a lot of that the climate models can't tell us. And so, of course, this is a place where we need a lot more research. In particular, in the Arctic, there's a real sparsity of observations because it's so cold. It's quite difficult to take observations, particularly in the winter. And so I will leave it. Yeah. So just to say that, I'm not trying to say anything too confidently.
Thank you, Haruki. That was really interesting. And finally, I'd like to welcome Alistair Duffey for our final presentation. Alistair is a PhD student based at University College London. He's researching how the Arctic climate would be impacted by solar geoengineering through stratospheric aerosol injection. His research interests also include Arctic atmosphere dynamics, as well as the links between Arctic change and climate change in the mid-latitudes. And before re-entering academia, he was working on decarbonising the building sector in the UK. So welcome, Alistair.
Thank you, Alice. And before I start, I just want to say a huge thank you to Operatio Arctis for putting this event together. I think it's a really unique and brilliantly put together event. It's just fantastic to see so many people here to discuss climate intervention. So I'm going to continue from where Haruki left us to talk about the second major contender for a means of achieving solar geoengineering, and that's stratospheric aerosol injection. Before I do so, I want to raise two facts, one of which you already heard from Kelly, and that's that volcanic eruptions cool the planet. Here you can see a plot of the temperature following the Mount Pinatubo eruption in 1991, and you see something like 0.5 degrees C of cooling that occurred after Mount Pinatubo added 15 million tons of sulfur dioxide to the high atmosphere. And that sulfur dioxide produced sulfate aerosols, small particles that reflected away sunlight, perhaps 1% less of the sunlight coming in, and that resulted in a surface cooling that lasted for several years. The second fact, again, we've mentioned this today, our current pollution masks warming. And globally, it masks something like 0.5 degrees Celsius of warming, but locally it can be much larger. The pollution is centered on the northern hemisphere, and it has the largest cooling impact on the very high latitudes. So although we're seeing maybe 0.5 degrees C of greenhouse gas warming masked by pollution. In the high latitude regions, it can be much more. Okay, so bearing those two facts in mind, let's think about SRM, solar radiation modification. This means reflecting away sunlight to reduce climate change. And within SRM, we can consider one proposal, which would be stratospheric aerosol injection, which means releasing aerosol particles or precursors to those particles into the stratosphere. So the stratosphere is the top part of the atmosphere, something like 15 kilometers up or higher. And it's called the stratosphere because it's stratified, which means that it's essentially split into layers and it's very stable. So when we add things to the stratosphere, they tend to stay there for quite a long time, perhaps several years. And that's why this idea has leverage. Particles added to the stratosphere would have a large impact on the planet for relatively low effort. And I think it's really important to stress that last bullet point here. The only reason to talk about these ideas is because they're easier than rapidly reducing our emissions to zero and then producing large-scale negative emissions. If they weren't easier, there would be no point talking about them. So I've put on the right-hand side there a graphic, sometimes called the napkin diagram, because supposedly someone once drew it on a napkin, and it describes like essentially plan A, or the best case version of why we might consider geoengineering. So working from the red line kind of downwards, you see BAU here is business as usual, perhaps an old-fashioned business as usual. Now this is quite a high emission scenario. And if we achieve net zero, we manage to get all the global emissions to zero. Everyone has a huge net zero party around the end of the century. At that point, we have to live with whatever the temperature is forever, if all that we do is we cut our emissions. So here we've sketched a scenario where maybe you get to net zero in 2100, and perhaps you have to live with 3 degrees Celsius of warming forever. And you have to live with all the effects of that, such as the ice sheets melting, which John told us so eloquently about, forever. Now, perhaps humanity might decide they don't want to do that, and they might then do a load of CDR, carbon dioxide removal, planting trees, perhaps using technology to do direct air capture, pulling carbon dioxide straight out of the air on large scales. And feasibly, maybe, they could do this over centuries. Right? It would take centuries to pull temperature back down towards another, say, 1.5 degrees Celsius. Now, humanity might decide they don't want to live at a warmer temperature over that period. So in this scenario, we imagine maybe they use SAI during those several hundred years to never have to deal with those warmer temperatures. In a way, that's kind of the best case vision for why we think this might potentially be a good idea. But of course, there's lots of reasons to doubt that. So when I was invited to give this talk, I was asked if perhaps I would spend a minute or two talking about why I work on this topic. So I think this figure is my attempt at explaining that. What you can see here is essentially a graphic which is taken from the introduction to a really excellent book on the topic by Oliver Morton called The Planet We Made. And he asks the reader to ask themselves 2 questions. How bad is climate change? And then the second question, how hard is it to cut emissions? Now, if you are someone that believes climate change is not very bad, the impacts are small, then of course you're not going to want to do climate intervention because it has a large set of risks associated with it. And if you're someone that thinks that getting to net zero is very easy and we could do it tomorrow, then of course you wouldn't consider climate intervention because we would just get to net zero tomorrow. But if, like me, you're someone that is very convinced that climate change is hugely harmful, but has a hunch that getting to net zero is also quite difficult and won't happen rapidly, then I would say to you that you have to consider the potential that climate intervention might make sense. And that's not to say you should be in favor of it today, but I would argue that we have to take it seriously. Cool, I've put a list there of a few reasons why you might be opposed to SRM. I think it's really important to note that talks like the one I'm giving are based on climate modeling. That's what the science of this is mostly based on. And climate modeling is quite good at producing maps of certain variables, but it's not very good at understanding whether conflict might arise because of an action that we take, or unforeseen risks that we haven't even thought of, or whether this will act as a distraction from emission cuts and we won't achieve emissions cuts targets. So this talk will, at times, address that first bullet point as a reason to be against this, but it won't address lots of other potential reasons that you might be opposed to climate intervention. Okay, so that's why you might be opposed to climate intervention. Why might you be in favor of it? Well, if you ask a climate model what happens under SAI, the first thing you'll notice, the thing that really stands out, is that the world gets colder, and lots of the changes that we're seeing under climate change are less. So here I've plotted one scenario for SAI. SAI is in red on the bottom axis, and the medium emission scenario, SSP 245, is climate science speak for a little bit like what we're doing today without much more action, is in blue. And you see on the right-hand side that towards the end of the century, after some amount of time of doing SAI, we have much more sea ice. And sea ice here is acting as an example for many climate variables, and the picture is often largely the same, that we see at least some restoration of those aspects of the climate system when we cool back towards the pre-industrial. Okay, so that's the first thing that you notice if you ask a climate model what happens. The second thing you notice is that SAI would not be a perfect offset of warming. Fundamentally, the climate system can tell the difference between reflecting sunlight and trapping more outgoing radiation with greenhouse gases. Those two things are not the same in the physics. And one example of that, which I think is quite a stark example, is with respect to rainfall or precipitation. So we know that with warming, with greenhouse gases, we intensify the hydrological cycle, and we expect the world to get wetter. And that's what you can see with this red circle here. As we go towards 4 times CO2, so in a world with lots more CO2, we have more warming, but we also have more precipitation. If we were to offset that warming by having less sunlight, you would move towards this blue circle. And you see a world that doesn't have the temperature change because the sun has been turned down in this scenario to offset the warming. But you can notice that the climate here notices the difference, and it's got less precipitation. Now, the reason for that is because essentially all your cooling is happening at the surface, where less sunlight hits the surface, whereas the warming is happening throughout the atmospheric column, where the greenhouse gases trap warming, and they act differently on the climate system. Now, this isn't to say that any scenario of climate intervention would see drastic reductions in precipitation. This is quite an extreme scenario that I've used to illustrate the point. But I think one key message to take home is that SRM in general would not get us back to the past. It would get us to some novel climate state that might have reduced harms associated with it relative to more warming, but it wouldn't be the past. And then I've also pointed out here that there is an option, even in this scenario, of this purple circle. And perhaps a sensible strategy in this case would be to go back to zero precipitation change, but not offset all the warming. And then continuing on that theme of imperfect offsets, another important point to make is that regionally, there would also be changes. We don't live in the global mean temperature, we live in a place, and there would not be exact restoration of the global climate regionally. In this case, again, I've taken a very simplified scenario where we've added CO2 and turned down the sun, and you see this kind of characteristic pattern in which there is residual warming in the polar regions, i.e. they're not cooled back to normal, while the tropics are cooled below normal in this case. Now, again, this is something that might well be avoided with more sophisticated methods of geoengineering. I'm thinking in particular, if you were to take aerosols and inject them more away from the equator and more towards the poles, you might avoid this result. But the key point that there would be regional changes, and we need to understand those, remains. And then lastly in my list of reasons this would be an imperfect offset of warming is seasonality. So we understand that SRM would have impacts on the seasonality of change, particularly in the polar regions. And one contribution to this is the simple fact that there isn't sunlight in the polar regions during winter to reflect, or very little sunlight. So if your method of cooling the planet is to reflect sunlight, then it will be less effective in the Arctic in the winter. And you can see that in these two plots, in which the blue line is our geoengineered world, and it's very good in the summer months, so August, September here, but we have somewhat less restoration of sea ice in the winter months. And there might be consequences to do with that dampening of the seasonal cycle that we could care about for ecological impacts, for example. Okay, so far I've kind of talked about SAI as being one thing, but the reality is it's not one thing. There will be options, and the design of SAI would be a crucial aspect of its impacts. And in particular, you can't design east to west with SAI, because the stratosphere has very strong winds that go east to west. So any particle you inject would very rapidly spread around the planet longitudinally. But there would be some ability to control the north to south pattern of cooling. In particular, the more that you injected aerosols towards the polar regions, the stronger your cooling would be towards the polar regions and the less it would be strong towards the equator. And this is just one model simulation showing that with injection at 60 degrees north, we're seeing quite strong cooling throughout the whole of the northern hemisphere, but particularly in the Arctic, and very little cooling in the southern hemisphere. So not much gets across the equator. But an important point to note there is that whilst you might mostly keep your cooling into one region of the planet, the impacts would spread around the globe. So here, I've shown a map of precipitation changes. This is Africa here, that's West Africa, that's the Arabian Peninsula, India. And what you're seeing is a really drastic reduction in the summer monsoon in this simulation for West Africa and India. Now, this is not a stress, an inevitable effect of climate intervention. This is, I think, John Wall referred to this kind of scenario as essentially a mad scenario. I can't remember the word he used, but this is a world where they've deliberately cooled down one hemisphere and not the other, and it creates essentially chaos in the dynamics of the circulation, resulting in these drastic drying of the low latitude in the northern hemisphere regions. But the important point to stress is that you can't expect to interfere with the climate system in one place and not have impacts everywhere. So here we're seeing localized cooling in the Arctic would have large implications for rainfall near the tropics. And then one last bit of science before I stop. I also want to stress that the climate system has processes which will essentially fight back if we try to do very localized interventions. So here I'm thinking about, in a case where we could only reflect sunlight over the Arctic, would we be able to achieve lots of cooling in the Arctic? Well, yes, potentially, but there are reasons why it might be quite difficult to do that. And one of them is to do with the heat transports in the atmosphere and the oceans. So on the left here, you see the globe. This is the equator, this is the pole, this is the Antarctic. And near the equator, we have more sunlight coming in than infrared radiation going out. And the energy has to go somewhere, and where it goes is it's transported by the atmosphere and the oceans towards the polar regions. So although the Arctic is cold, it's not as cold as it would be if we didn't have an atmosphere and an ocean transporting heat towards it. And then in the Arctic, the opposite happens. And because we've got heat coming in, more radiation is emitted to space than is received from the sun. Now, the reason for that heat flux is because this part is colder than this part, and heat travels towards the cold from the warm place. If we then were to run scenarios of cooling the Arctic and only the Arctic by turning the sun down northward of 60 or 70 degree north in our climate model, what we find is, unsurprisingly, if you cool a lot locally, the planet will transfer more heat to that cold spot. And so your local cooling is undermined by these compensating heat fluxes. So the key point here is that although it might be possible, potentially, to do solar reflection very locally and have an impact, you have to have very strong local reflections to achieve cooling because the Earth will kind of fight back and transfer more heat to that cold spot. Okay, I'm going to leave it there and give you these 3 take-home messages. So firstly, SAI would almost certainly cool the planet, including the Arctic. But as Haruki stressed, we need to know more. There are lots of known unknowns and presumably many unknown unknowns too. And then lastly, SAI with injection at higher latitudes would likely more effectively restore the Arctic climate on a kind of per amount of sulfate injected basis. But we would still have to think of that as global geoengineering. There aren't really any plausible ways in which you could cool the Arctic and only the Arctic by reflecting the sunlight and have no impacts everywhere else. Cool, I'll stop there.
Thank you, Alistair. That was a fantastic presentation. So I think now we're going to have just a few questions. based on those, because that was fascinating, and I definitely want to hear some more. So I think, Kelly, we'll start with you, if that's okay. In your talk, you mentioned sort of the governance around solar radiation management or modification and climate intervention. How could civil society better support that research and governance also for climate interventions?
Well, thank you for the question, Alex. We had that question come up in the workshop previously, so I had some prompting as well for that. But I think that civil society being, the nonprofit organizations and activists and people, and I think that Operation Arctis has given us a tremendous example here of how to articulate where we are currently in real terms. And so I think civil society, in terms of being advocates for young people, for the harm that is now happening and that is very proximate, and that we have to, in some ways, Annie put it so well, we have to do away with some of what we hoped was going to be the paradigm for this and look at a new paradigm quickly. So I think that civil society groups, and especially those youth-led organizations where, again, Annie put it well, you're stepping in to the situation. You're 22 years old, you're 24 years old, and you're walking into this reality. And so there's certainly a way in which that, helping the older generation, clarify what's needed, and then, and then advocating for science and information, that, this is a very serious safety situation. We need a lot of scientific evidence fast. And so going to policymakers, going to the media with these messages, I think is really, really helpful.
Yeah, that's great, thank you. I guess touching on that also, it seems like one of the best things we could do to sort of better assess these risks of research. How do we go about trying to involve more people in that research? I guess any of you guys want to answer that question.
Well, I'll just say a quick word, since I know we have some policymakers here and some folks who want to help, but definitely funding is a question. And so for both philanthropy and for government sources of funding, like moving funding into specifically research on interventions, but also some of the basic science and these uncertainties that they referred to and how aerosols and these factors work in the climate system is absolutely crucial. So we have to move some money to support the research for scientists like these.
Okay, well, I guess one thing I would say is that, I think most people who work on climate modeling, in particular for SRM, tend to be trained as either meteorologists, perhaps, or as physicists, and that means that the climate models tend to be good at things like temperature and precipitation, and these are obviously very important, but they're not the whole picture in terms of the climate impacts. And so I guess what I would say is that I think it's really important that, I guess, tell us what is important for you and what we should be looking for. And, there's a lot of things that we could put in our models that, maybe we just decide is not important or not worth putting effort into, but maybe we should be. And yeah, I think that would be very helpful to know what we should be looking for.
I guess one thing I would add is, it's been said a couple of times in the workshop in the last few days that perhaps in the generation before us in science, there was a feeling that working on this was just a death knell for your career. This was a bad thing to work on, and you wouldn't get jobs, you wouldn't get funding, and that I think is changing, but it needs to change more rapidly. And there's a huge untapped potential of expertise of climate science that is not working on this problem, which it could be used, and we have to find ways to kind of break the taboo around this in the scientific community to bring those experts in and widen our community of people working on this, which is still really quite a small field.
Yeah, that's great. I guess also there are probably quite a lot of risks associated with stratospheric aerosol injection or marine cloud brightening that are kind of the uncertainties in the models are down to sort of research gaps in general climate change itself. What would you say would be the most critical risks with solar climate intervention, either in modeling or ecological or social aspects?
I guess I can, in my own opinion, and this is just an opinion, the most important risks with SRM are not the physical climate risks. They are the socio-political risks, the risk of conflict, the risk of militarization, the risk of accidentally starting a war. That's what I really worry about. But of course, there are physical climate risks too. But that's just my opinion.
Okay, I guess, yeah, again, sort of reiterating the point that, of course, we know a little bit about the physical climate risks, but, you know, we are adding things to the atmosphere, whether it's MCB or SAI, and these will also have knock-on effects on the chemistry as well as biology. And so I think, yeah, so the risks, I think, are in those unknown unknowns, in those kinds of sectors where we simply don't know what the risks could be, I suppose.
And kind of echoing that and looking at some of these mechanisms for decision-making that call on science, you know, and then looking at the work from Alistair, Haruki, yourself, Alice, like these early modeling studies that show such differences in different kinds of impacts depending on how you might do this, what regions of clouds you brighten, what latitudes, and you get some really interesting side effect differences. So we think about it like medicine. And right now we have these treatment options, and we know little something about their efficacy and really not enough about their side effects. And so I think the physical risk profiles, you know, they're linked up to your concerns, Alistair, which is, are people afraid, you know, that they're going to be on the downside of these side effects to somebody else's benefit? Or can we all see this together? And if we can all see it together, then, you know, maybe some of the risks you're talking about get muted.
Yeah, absolutely. So I guess kind of, I mean, for me personally, the last couple of days, the main takeaway has been we kind of need some more research in this area. But obviously, that will only come with time, and hopefully we can solve some of these problems. I guess when we sort of talk about solar climate intervention, one of the risks that I've seen in the past when talking with colleagues is I think, Alistair, you touched on it, the idea that we may not, or people may not then think we need to do anything else. Like it's seen as an alternative, it's an easy option. How do you guys all feel about how the role of solar climate intervention sits within that bigger climate issue and how we tackle these sort of bigger problems?
I can start, since I've talked to people about this, and some of those interactions haven't been like you might anticipate. So I think one of the things about research and dialogues like this in climate intervention, you know, they're really calling to the forefront how acute the risk is, and just where the situation is at. And if listening to Anni's talk, like I think the dialogue's kind of moving on from is it mitigation or intervention? It's, well, mitigation is absolutely necessary because, you know, using the cancer analogy, if we're going to do climate intervention, and one of the things that their work shows is actually less is more. Like the less you do, the lower the side effect risk is. So I think there's some ways in which this kind of research can really help highlight what exactly is happening in a way that propels people, hopefully. And also, again, to a point that Anni made beautifully, which is that these escalating impacts are not going to help us in our mitigation efforts. People are suffering, they're desperate. These are really expensive things to happen and really tragic. So it may be that, you know, in keeping the system more stable, that we actually promote some of the mitigation efforts that we're trying to do as well.
So sort of using it to fuel motivation to mitigate more rather than trying to push the can
Yeah, to
down the
fuel
road.
motivation and reduce desperation.
Yeah.
And leave some resources free for us to do the transition that we need to do and the science that we need to do.
Do you guys have anything to add on that?
No, I think I would echo what Kelly said, really. I think we have to take seriously the worry that there is a very bad scenario where you have a bigger and bigger layer of aerosols because the world is not cutting emissions, and you end up living under this Damocles sword of warming hanging over you forever because you've not got to net zero. And that is something we have to take seriously. But yeah, maybe we have to be optimistic that the world could manage to do both. And we did say very similar things about adaptation back in the 1990s, that we shouldn't adapt, or we can't talk about adapting to climate change because then we won't cut emissions. And that sounds kind of silly to us now. We clearly have to cut emissions whilst adapting to climate change. And perhaps we've been making the same mistake again to give up on soil climate intervention because of that risk.
Yeah, I don't have anything to add.
Yeah.
Well said, Kelly.
Brilliant. Well, I'll just wrap up then. This was a fantastic discussion. Thank you all for sharing your perspectives and contributing to this event. And thank you for having us.